Hello everyone, let me introduce myself. My name is Maharani Putri. You can call me Lani. My student ID is 21029023. I will explain about the Chinese remainder theorem.
Hello, my name is Rahma Sinta. You can call me Sinta. My name is 21029107. I will read the second slide.
Hello, my name is Ryo Praditya Hendrinata with student ID card 210291115 from Mathematics Education Study Program. I will explain about Chinese remainder theorem, slide 3.
Hello everyone, my name is Muhammad Ilham Adya. You can call me Ilham. With collect student ID number is 2102916 and 3. I will explain the first slides of the Chinese remainder theorem.
Hello guys, my name is Natasya Pratiwi. You can call me Tasya. My student ID number is 21029099. Okay, in this part, I will explain the fifth slide.
Hey everyone, my name is Nasywa Salsapido. You can call me Nasywa, and my student ID number is 21029194. And I will read material about the Chinese remainder theorem.
Hello everyone, my name is Revatri Angraini Nst. My student ID number is 21029175. I will explain about the Chinese remainder theorem on slide 7.
Hi guys, I'm Reasty Amanda with student ID number 21029111 from Mathematics Education. I'll explain about slide 8.
Hello everyone, let me introduce myself. My name is Marsha Habibah. My student ID is 21029091. Okay, I will explain an example of problem from the Chinese remainder theorem.
Hello guys, my name is Nabila Nuraisyah, name 21029167. My material is the remainder Chinese theorem.
Hello, my name is Septi Marwiyah, student ID number 2102939. Here I will explain about example number 3 in the Chinese remainder theorem. Thank you.
The Chinese remainder theorem. We start by considering a typical problem that can be solved easily with the help of the Chinese remainder theorem. You are invited to try it before looking at the methods of solution. One given immediately afterwards and another using the theorem at the end of the section. Appetizer problem. Brilliant duck in Bertrand Carroll's fiction book Madeline was inch brilliant. She devised a quick way of counting her ducklings, which was basically a residue evaluation process after division separately by 5, 3, and 11. She knew that 1. When counted by 5, 2 ducklings remain. 2. When counted by 3s, 2 ducklings remain. 3. When counted by 11s, 3 ducklings remain. The next slides will explain by Rahma Sinta.
What is the smallest possible number of ducklings she has? Please spend some time on this problem before reading on. Intuitive approach to appetizer problem. Your checking may have revealed that the number of ducklings is given by the number which occurs in each of the following arithmetic sequence: 2, 7, 12, 17, blah blah blah, 2 plus 5p, 2, 5, 8, 11, blah blah blah, 2 plus 3k, 3, 14, 25, 36, blah blah, 3 plus 11 are. The smallest common number 47 can be found by developing those sequences a little and occurs when
E equal 9, D equal 15, and R equal 4. Therefore, billion duck has 47 ducklings.
I will explain about the Chinese remainder theorem slide 3. Such comparison of sequences can be a very handy tool for rapidly solving problems such as the brilliant duck problem. However, the method may be cumbersome and is not general. It might fail altogether in some cases. Examples of such situations include 1. The smallest common term may be given by very large value of P, K, and R, so large that even the most deep or tuned teller will not have a clue where to start. 2. Many more than 3 sequences, as in this example, may be necessary. And the last, a combination of 1 and 2 is example a real nightmare. Thank you. And the last, a combination of 1 and 2 is example a real nightmare. Thank you. The next slide will explain by Ilham.
A more systematic approach to solving brilliant ducks and related problems is given by the following. Theorem 6. The Chinese remainder theorem. Suppose we wish to find a number x which leaves a remainder of R1 when divided by D1, a remainder of R2 when divided by D2, until n a remainder of Rn when divided by Dn, where no two of the divisor D1, D2 until Dn have any factors in common. Let D equal D1, D2 until Dn, and yi equal to D over di. Now, if we can find numbers a such that ai, yi equivalent with 1 mod di for each I 1 smaller than I smaller than n.
Then a solution to our problem is x is equals to a1 times y1 times r1 plus a2 times y2 times r2 plus an yn rn is equals to sigma I equals 0 to the n ai times yi times ri. Remarked, we have used the summation notation explained in 2G6. Note that there are infinitely many possible values of x satisfying the conditions above. For if x0 is a solution, then so is x0 plus minus k times d, k element z. We shall, however, limit ourselves to the smallest positive value satisfying the required conditions. Proof: we have to show that for each I running from 1 to n, x leaves a remainder ri when divided by di. Consider for each j more than or equals to 1 and less than or equal to n, and I more than or equals to 1 and less than or equal to n. So m is equals to ai times yi times ri all over di is equals to ai times d times ri all over di times dg. Okay, next slides will explain by Nasywa.
The Chinese remainder theorem. If I not equal to G, then multiplied by dg t so that M belongs to Z. However, if I equal G, then di multiplied by dj does not divide D, since none of D1, D2, and Dn share any common factor, hence M not belongs to Z. This shows us that if and sum of I equal to 0 multiplied by AI multiplied by yi and multiplied by ri is divided by dj. Every term other than the jth term is a multiple of dj and hence leaves a remainder of 0 when divided by dj. Hence, to obtain the remainder when x is divided by dj, we only need consider the jth term, aj multiplied by yj multiplied by rj. Now, by choice of the number aj multiplied yj equivalent to 1 mod dj, and hence aj multiplied by yj and multiplied by rj equivalent by rj mod dj. We now use the Chinese remainder theorem to solve the billion duck problem above. Next, the material that will be read by Revatri Angraini.
The Chinese remainder theorem, slide 7. Solution of appetizer problem. We have D equal D1 times D2 times D3 equal 5 times 3 times 11 equal 165, and from yi equal dy over di. We have y1 equal 165 over 5 equal 33, y2 equal 165 over 3 equal 55, y3 equal 165 over 11 equal 15. It remains to find a1 such that 33 a1 minus 1 is divisible by 5, a2 such that 55 a2 minus 1 is divisible by 3, and a3 such that 15 a3 minus 1 is divisible by 11. It should be easy to see that a1 equal 2, a2 equal 1, and a3 equal 3 give the desired result. It's now a simple method to evaluate x, which is given by x equal sigma I equal 0 and ai yi ri equal a1 y1 r1 plus a2 y2 r2 plus a3 y3 i3 equal 2 times 33 times 2 plus 1 times 55 times 2 plus 3 times 15 times 3 equal 132 plus 110 plus 135 equal 377.
Okay, I'll explain about slide 8. Know any number of the form 377 plus minus 165k is the solution. However, to get the smallest possible solution, we set k equals 2 to obtain 377 minus 330 equals 47 as before that we know from slide 2. The working could be neatly laid out in tabular form as shown below. We know that I is index. We get index from substitute 1, 2, and 3 into I. DI is divider, RI is remainder. We get DI and RI from the statement in slide 1. YI is the result from D divided by remainder. AI is the number that if multiplied by YI and then reduced by 1 can be divided by DI. AI YI RI is the result from AI times YI times RI. We get YI, AI, YI RI from slide 7. After substitute all number, we can find the sum from I equals 0 to n of AI YI RI equals X equals 377. We know that D is 5 times 3 times 11 equals 165. So take 377 minus 165 times 2 equals 47 that we know before. The next slide will be explained by Marsha.
Okay, first sample question is, suppose n is the biggest 3-digit number, a remainder 2 when divided by 5, a remainder 1 when divided by 3, and a remainder 5 when divided by 8. Define n value. Write it in modulo form. Because a remainder 2 when divided by 5, then n is 2 modulo 5. Next, n is 1 modulo 3. Next, n is 5 modulo 8. The first solution is we need to find the least common multiple of 5, 3, and 8. And the least common multiple of 5, 3, and 8 is 120. So, we can make all the modulus 120. The first multiply by 24 to all, so that this 5 becomes 120. That is 24 n is 48 modulus 120. The second multiply by 40, so 40n is 40 modulus 120. The last we multiply by 15, so 15n is 75 modulus 120. From here, we can determine n. The way we can multiply it is 24n, 40n, and 15n. My times, my add, may be less, but should not be subdivided. The condition is that the 24n, 40n, and 50n must all be 1. So we can determine that n is 4 times 24n minus 2 times 40n minus 1 times 15n. So that we can get 4 times 48 minus 2 times 40 minus 1 times 75 modulus 120. 192 minus 80 minus 75 modulus 120. So n is 37 modulus 120. So we can write n is 37 modulus 120 equals 120k plus 37. It depends on the question. If you say positive circles, it starts at 0. the question n is the 3 digits largest. We should use the 3 biggest digits, that is 999. From here, we must determine what this k is to become the largest 3-digit number. If k is 7 and then n is 877, then his n is small. We choose k is 8, then n is 997. So the biggest 3-digit number is that 997. Thank you.
Problems 2. Given the notation x for positive integers, if it's divided by 3, then the remainder is 1. If it's divided by 9, then the remainder is 1. If it's divided by 12, then the remainder is 7. If it's divided by 14, then the remainder is 7. The question is, can the number be found? Answer. We will rewrite the statement in problems as below. X equals to 1 mod 3. X equals 1 mod 9. 3x equals to 7 mod 3. And the last, x equals to 7 mod 9. Because the question is only does the value of x exist, so what we do now is just check using the Chinese remainder theorem. Cypress 1 and 2, 1 1 is divisible by 9 3, so 0 is divisible by 3, so true. Cypress 1 and 3, 7 1 is divisible by 12 3, so 6 is divisible by 3, so true. Cypress 1 and 4, 7 1 is divisible by 14 3, so 6 is divisible by 1, so true. Cypress 2 and 3, 7 1 is divisible by 12 9, so 6 is divisible by 3, so true. Cypress 2 and 4, 7 1 is divisible by 14 9, so 6 is divisible by 1, so true. Cypress 3 and 4, 7 7 is divisible by 14 12, so 0 is divisible by 2, so true. Because all checks are true, then of course the value of x exists and can be searched. Thank you. The next material is problems 3.
Problem 3. The following number which when divided by 3, 5 and 7 effectively give a remainder 1, 2 and 3 are A 42, B 52, C 62, D 72, E 82. Discussion. Express the following system of linear congruence: x equals 1, x equals 2, x equals 3. Notice that the numbers are relatively proximate to each other, so the system has a solution. For m equals 3 times 5 times 7 times 105, we get m1 equals 105